Imagine having a brilliant idea for like a life-saving drug or maybe a revolutionary new solar panel material.
Right.
You have a whole hypothesis mapped out. You were totally ready to test it, but you can't.
Yeah, it's frustrating.
And it's not because your science is bad. It's simply because your lab is short about, $95,000.
Yeah. And that is just the uncomfortable reality of modern chemistry right now. I mean, we like to view science as this pure meritocracy where the best ideas win.
Right. The whole cream rises to the top thing.
Exactly. But the actual bouncer at the door of elite scientific discovery is incredibly expensive hardware.
Which is essentially the Matthew effect in action, right?
Right.
The old adage that the rich get richer.
Precisely.
Because right now, if you want to aggressively discover new breakthroughs, you need a self-driving laboratory, an SDL.
Yeah, and those are incredible. I mean, there are these massive robotic systems that automate chemical reactions nonstop, and they're guided by artificial intelligence.
But they are massive,
Yeah.
right? Pristine, and they cost upwards of $100,000.
Oh, easily. And that's not even counting the analytical equipment attached to them.
So the well-funded labs at these massive universities or, big pharma companies, they buy these machines.
Right, and then they run thousands of experiments overnight.
Yeah, they publish groundbreaking papers at lightning speed. They secure more grant money with those papers. And
With
then
not even more equipment.
Exactly. Leaving resource-limited labs like community colleges, smaller universities, researchers in developing nations completely in the dust.
The gap just keeps widening.
But, and this is why we are here today, we're looking at a potential earthquake in that landscape. We're doing a deep dive into this groundbreaking April 2026 paper from Nature Synthesis.
Yeah, this paper is huge.
It introduces a platform called RoboChem-Flex, which is an automated AI-driven chemistry robot, but it only costs about $5,000.
Right. Because it is entirely open source, it relies heavily on 3D printed parts, and it uses off-the-shelf microcontrollers.
Okay, let's unpack this. Because jumping from a $100,000 immaculate robotic facility to a $5,000 DIY setup sounds like you were going to lose all the actual science in the process.
Yeah, it sounds like a toy.
Right. So how does this thing actually work without just falling apart?
Well, you have to completely rethink the physical architecture. I mean, the barrier with current self-driving labs isn't just the price tag, right?
Well,
it's the multidisciplinary expertise required. To keep those commercial machines running, you usually need PhD-level experts in robotics, fluid dynamics, custom software.
just keep your lights on, basically.
Exactly. But RoboChem-Flex sidesteps that by acting more like high-end Lego. The core brains of the physical movement are Arduino Uno microcontrollers.
Wait, Arduino's the same little blue circuit boards high school kids use to build robot cars?
The exact same ones. I mean, they cost a few dollars each.
Wow.
But when you combine them with custom 3D printed parts and really smart open source Python software, you get staggering precision.
Let's talk about the hardware first.
Yeah.
The brawn of the operation, if you will. Because they aren't dumping liters of expensive chemicals into giant vats, are they?
No. They use a system called a slug flow regime.
Okay, slug flow. Let's use a visual memory trigger for you listening. Picture looking through a tiny transparent straw.
Right.
Inside that straw, the robot creates a segmented train of chemical carriages. You have a tiny droplet of liquid, which is the slug, followed by a little bubble of inert argon gas, followed by another droplet of liquid.
Yeah, and that gas bubble acts as a physical wall. It completely prevents the different experiments from mixing together.
Oh, and it probably sweeps the tube clean as it moves.
Exactly. It pushes everything along. Because of this, the robot can run massive numbers of distinct isolated experiments using just like 5 to 50 micromoles of material per run.
Which is practically microscopic.
Right.
And that alone slashes the budget for raw chemical regions.
Yeah.
But to push those tiny trains through the tubes, you need serious precision. And commercial syringe pumps that handle microliters of fluid are notoriously expensive.
Right. And this is where the engineering gets really clever. They obviously couldn't afford commercial pumps, so they built their own.
Out of what?
They used standard trapezoidal lead screws and linear ball bearings.
Okay, break that down for someone who isn't a mechanical engineer. How does a lead screw replace a high-end pump?
Think of a standard car jack. You know, the one in your trunk.
Yeah.
You have a threaded metal rod. As you turn that rod, the rotational motion is converted into a very slow, incredibly strong and highly precise straight push.
Oh, that makes sense.
So they used cheap stepper motors to turn these lead screws, which physically push the syringes.
But a cheap motor can skip a step, right?
Yeah.
Or jam up.
Exactly. So to fix that, they added integrated magnetic encoders and end-of-travel sensors.
So the pump essentially knows exactly where it is at all times.
Yeah, it creates a closed feedback loop. If there is a blockage in the tube and the pressure builds up, the sensor detects that the motor didn't move as far as it was supposed to. It immediately stops and alerts the user, rather than, snapping the plastic or blowing out the tubing.
That is brilliant. And to actually move the sampling needles around, I read they used cheap, commercially available 3-axis Cartesian robots.
Yeah.
Just basic moving arms that you'd find in a cheap 3D printer, modified with custom 3D printed sampler heads to handle liquids.
Right.
But I have to push back here.
Okay, go for it.
If we are dealing with complex organic chemistry like harsh solvents, corrosive acids, high temperatures, isn't a robot made of cheap 3D printed plastic and high school microcontrollers just going to melt into a puddle on day 2?
Well, yeah, that would definitely happen if they used standard PLA plastic.
Right.
But they didn't. They printed the components using PETG, which has significantly higher chemical and thermal resistance.
Okay.
Furthermore, the chemical vials aren't just sitting open to the air, getting fumes everywhere. They are sealed with standard septum caps.
Ah, so the robot needles just pierce, and they also have a dedicated inner gas line flushing the system to keep moisture and oxygen out, right?
Yeah, so they completely bypassed the need for an expensive sealed glove box. They even manufactured custom-printed circuit boards, PCBs, that all those Arduinos plug into.
So no messy wires everywhere.
Right. It eliminates the mess of loose cabling you usually see in DIY projects, which dramatically improves electrical safety and reliability in a wet lab.
Wow. Let's do a quick mini recap for you listening, because that was a lot of engineering.
Let's do it.
First bullet point. The Matthew effect in science, the rich getting richer, is actively being disrupted by a $5,000 robotic lab.
Second bullet. They achieve this by combining slug flow hardware with clever, cheap engineering like lead screws and PTG plastic to create a plug-and-play system.
So here's an interactive question for you, the listener. Think about your own field. What is that one obscenely expensive piece of equipment that keeps beginners out? And how could open source tech theoretically replace it?
It's a great question, because the hardware is only half the battle, really.
Right. A robot arm is completely useless without instructions.
Exactly.
So let's talk about the brains. The software side is divided into 2 parts. First, you have Omniplatypus.
Which is a fantastic name.
It sounds like a cartoon character, but it is actually the hardware controller. It operates on what they call unit tasks.
Right.
I try to think of these as atomic actions. Basic, irreducible commands like fill a syringe with X volume or move needle to coordinate Y. You string these basic atomic actions together to build a complex chemical recipe.
Yeah, Omniplatypus just follows orders. It's the muscle. The real genius, the higher level brain, is a Python package they developed called RoBrains.
RoBrains.
This is the artificial intelligence Bayesian optimization engine, and it's built on a machine learning framework called BoTorch.
Okay.
RoBrains is the actual scientist. It decides which experiments to run next.
But when you boot this thing up for a brand new reaction, the AI has 0 data, right? It's completely blind.
Totally blind.
So it uses a technique called Latin hypercube sampling, or LHS, to choose the very first batch of experiments.
Yeah, and how would you visualize LHS for someone new to the concept?
Well, I use an analogy. I picture it like trying to find the absolute highest peak in a massive, jagged mountain range.
Okay.
But the entire area is covered in thick fog. You have absolutely no idea where the summit is.
Right.
Latin hypercube sampling is like dropping a team of parachutists evenly across the entire mountain range. You mathematically force them to scatter.
I love that.
They scout the broad area, taking altitude readings, so you get a rough lay of the land before you commit to hiking up one specific slope.
That is a perfect way to look at it, because once those initial parachutists report back, meaning the first few random experiments are analyzed, RoBrains uses that data to build a mathematical model of the mountain.
And then it has to start making actual decisions.
Right, and chemistry, like anything else, is full of trade-offs.
Which brings us to the first major case study. The first hurdle the researchers threw at RoboChem-Flex was a photocatalytic trifluoromethylation.
That's a mouthful.
It is. Basically, they were using light to forcefully attach a specific cluster of atoms onto a ring-shaped molecule.
Right. and they hooked the robot up to an inline NMR spectrometer to get real-time feedback on how well the reaction was working.
Okay.
To optimize this, the RoBrain's AI used what is known as an upper confidence bound, or UCB, algorithm.
UCB.
Yes. And this algorithm's entire purpose is to manage the tension between exploration and exploitation.
Okay, that's the classic restaurant dilemma. Let's explain that.
Yeah, go ahead.
Imagine you are trying to pick a place for dinner. You have a favorite neighborhood spot where, for a fact, the food is an 8 out of 10.
Always solid.
Right. Going there is exploitation. You are exploiting known good data to get a highly reliable result.
Makes sense.
But there's a brand new place across town you've never tried. It might be a 10 out of 10, or it might give you food poisoning. Trying it is exploration.
Exactly. And the AI is constantly running that calculation. Do I slightly tweak the temperature on a reaction that I already know gives a 60% yield? That's exploitation.
Or do I completely change the catalyst and the solvent to explore a totally unknown area that might give an 80% yield?
Right. And the software handles this with an adaptive, variance-driven mechanism.
What does that look like in practice?
Well, during this specific reaction, the robot ran 3 consecutive experiments, and it hit a plateau. The yields were all hovering around the same number.
Like it wasn't getting any better.
Right. The AI realized it was stuck on a false peak, a local optimum on your mountain range.
Okay.
So it actively changed its own mathematical bias. It stopped exploiting that local area and forced itself to explore radically different chemical conditions.
And it paid off immensely, right?
Oh, huge. By breaking out of that plateau, it found a unique set of conditions that produced a 71% yield in just 2 minutes of reaction time.
2 minutes. Wait, what was the standard for that?
To put that in perspective, the existing literature benchmarks for this exact reaction required either 5 hours to hit that 71% yield or 3 minutes to get a much lower yield.
That is insane. The $5,000 robot crushed the human benchmark.
What's fascinating here is how the software adapts its strategy based on the specific type of chemical problem.
Right, because maximizing one good thing is relatively easy.
Exactly.
But what happens when you want to make one specific product, but absolutely avoid a side product that is chemically very similar?
That is much harder.
And that was their second case study, a deoxygenative CH functionalization.
Right. So the goal here was to attach an alkyl group to a specific molecule, but the molecule had 2 vulnerable spots.
So it could attach in the wrong place.
Yeah. They wanted the monoalkylated product attaching just one group, but they had to strictly avoid the dialkylated product, where 2 groups accidentally attach.
Yeah, that ruins the whole batch.
Completely ruins it.
So how do you tell a robot to maximize X while simultaneously minimizing Y?
This moves us from simple optimization to a hypervolume optimization problem. The AI switched its acquisition function to something called key HVI, which stands for expected hypervolume improvement.
Okay, key HVI.
But more importantly, it paired that function with random forest surrogate models.
Random forest. Wait, most AI optimization uses Gaussian models, right? Why switch here?
Well, Gaussian models are fantastic for smooth, continuous data, like slowly turning up the temperature from 20 to 100 degrees.
Right, it's a smooth curve.
Exactly. But chemistry has categorical variables. You might have to choose between solid catalyst A, catalyst B, or catalyst C.
Oh, I see.
There is no smooth mathematical transition between completely different solid powders.
Yeah.
Gaussian models struggle with that.
But a random forest model thrives on it.
Yes. A random forest creates a multitude of decision trees that can easily categorize discrete choices. It maps out the trade-offs mathematically.
So it's plotting a curve to find the absolute sweet spot, the point where you get the most monoalkylated product with the least dialkylated waste.
Exactly. And again, it worked. The robot achieved a 58% yield of the desired product with an incredibly high 94% selectivity.
It successfully dodged that unwanted side product almost completely.
It did.
Okay, let's do our second mini recap.
Sounds good.
Bullet point 1. The AI uses an adaptive UCB algorithm to balance exploring new conditions with exploiting known good ones.
In bullet point 2, hypervolume optimization allows the robot to maximize a desired product while simultaneously minimizing unwanted side products.
So here's our interactive question for this section. If you were programming this AI, for your own projects, would you prioritize discovering a totally new wild reaction, or would you prioritize perfecting an existing stable one?
The balance is everything. But, we really have to address a massive elephant in the room here.
Oh, what's that?
It is relatively easy for an AI to make smart choices when it is being fed perfect, clean data from a $50,000 inline NMR spectrometer.
Oh, right, because in these first two cases, it had pristine feedback.
Exactly. But real-world labs, especially the resource-limited ones this robot is built for, they have cheap, noisy analytical equipment.
Which brings us to case study 3, where things get extremely messy. Because high-end analyzers are usually the bottleneck.
Always.
So the team built a low-cost DIY Raman spectrometer using off-the-shelf camera parts and lasers to analyze a hydrogen-deuterium exchange reaction.
Right. Basically, they were trying to swap out a standard hydrogen atom for its heavier cousin deuterium.
But the issue with a cheap DIY spectrometer is that the data quality is atrocious.
Oh, it's terrible. It has low spectral resolution, and the signal-to-noise ratio is awful.
Right.
But worse, the noise isn't even consistent. The amount of random noise actually changes depending on the chemical concentration in the sample.
Oh, wow.
Yeah, this is known mathematically as heteroscedastic noise. Hetero meaning different, scedastic meaning scatter.
Okay, so if the sensor is cheap, the data is essentially garbage. How does an AI optimize garbage?
That's the challenge.
Because if it trusts that noisy data implicitly, won't it just start chasing ghosts? I mean, it might think it found a brilliant reaction, but it's actually just a glitch in the cheap camera sensor.
Precisely. You have to teach the AI to actively doubt its own senses.
Wow. How?
To do this, they used a mathematical function called a clogeny, HD, which stands for logarithmic noisy expected hypervolume improvement.
Okay, that is a terrifying acronym. Let's translate that for everyone listening.
Sure. Before the optimization started, they fed the AI calibration curve.
Okay.
These curves showed the AI exactly how error-prone the cheap sensor was at different concentrations.
Oh, I see.
So when the AI takes a reading, it doesn't just see 80% yield, it sees 80% yield, but because of the concentration, I know there's a 15% margin of error here.
It mathematically compensates for the cheap hardware.
Exactly. It prioritizes data points that are genuinely informative rather than getting distracted by a point that looks optimal purely because of a random noise spike.
That is wild.
And by understanding its own hardware's limitations, the system found conditions giving a 70% yield and 71% deuterium incorporation.
Beating the previous records.
It vastly beat the previous published records, which had maxed out at just 38%.
Here's where it gets really interesting to me. Because not every lab can connect their robot directly to any analyzer, cheap or not.
Right. Sometimes the machine is in another building.
Exactly. Often the analytical machine is down the hall in a shared facility. And case study 4 looked at exactly this with a human-in-the-loop approach to biocatalysis.
Yeah. In this one, they were using enzymes, alcohol dehydrogenase, or ADHs, to drive a reaction.
Okay.
But the analysis required a UHPLC machine that physically could not be connected to the robot. So the robot couldn't get real-time feedback.
It had to run the reactions and wait for a human to carry the samples down the hall.
Exactly.
But wait, if a reaction just sits there waiting for a human, it keeps reacting right, the data will be completely wrong by the time it gets tested.
You're absolutely right. So the robot autonomously quenched the samples.
Crunched them.
Yeah. After the programmed reaction time, the robot dropped the samples into vials preloaded with SDS.
What's SDS?
SDS is a surfactant, essentially a very heavy-duty soap.
Okay.
It instantly denatures the protein enzymes. It unwinds their physical structure, which immediately stops the chemical reaction dead in its tracks.
Oh, so it basically freezes the reaction in time so the human can analyze it whenever they are ready.
Exactly. The human gets the data, types the numbers into the RoBrain's web interface, and the AI calculates the next batch.
But because humans are slow, you don't want to run one experiment at a time, right?
No, that would take forever. They ran batches of 4.
Okay, but when you run a batch, you don't want the AI to select 4 nearly identical experiments. That's a waste of the human's time.
Right. So they used dual acquisition batching.
What does that mean?
Half of the batch 2 experiments were selected using our old friend, the UCB function, aiming strictly for the highest predicted yield.
Okay, so that's exploitation.
Right. But the other 2 experiments in the batch were selected using a function called QINPV.
QINPV.
Yes. And this function ignores predicted yield entirely. It specifically targets areas of the chemical space where the AI's mathematical model has the highest uncertainty.
So pure exploration.
Exactly.
It's an elegant way to cover your bases while waiting on a human.
It really is.
Time for recap number 3.
Let's do it.
Bullet 1. The AI can mathematically compensate for cheap, noisy analytical equipment by doubting its own sensors.
And Bullet 2. The system allows a human in the loop to bridge the gap between automated synthesis and shared offline analytical machines.
So for you listening, here's a question. It's fascinating how software can patch the holes of physical limitations. Where else could AI be used to clean up noisy data from cheat hardware in our daily lives?
We see it in smartphone cameras already, right?
Yeah, exactly. But the industrial applications are staggering.
They really are. And this actually leads us to the pinnacle of what this software can do.
Segment 4.
Right. We've seen it handle noise, we've seen it wait for humans. But case study 5 showed it performing high-level thinking by applying past knowledge to completely new problems.
Which is called transfer learning.
Exactly. They applied this to the Buchwald-Hartwig emanation.
Okay, let's explain that. This is a cornerstone reaction in synthetic chemistry for building carbon-nitrogen bonds, right? Which are the backbone of countless pharmaceuticals.
Yeah, it's hugely important. But finding the right catalyst for it usually requires screening dozens of expensive options.
Right.
To map out these complex catalysts, the AI used UMP ligand featurization.
UM.
Yes. UMP is an algorithm that takes insanely complex multidimensional data and simplifies it so the AI can process it efficiently.
I try to visualize UMAP like taking a 3D topographic globe of the Earth.
Okay.
With all its mountains, ocean, trenches, and valleys, right? And mathematically flattening it out into a 2D paper map.
That's exactly what it does.
The AI takes the highly complex 3D quantum mechanical properties of these chemical catalysts and flattens them into a 2D mathematical space.
Right. And by doing this, the AI can actually see which underlying physical features of the catalyst matter most for driving the reaction.
Okay, so using that 2D map, the robot optimized a specific molecule, we'll just call it product 12.
Right.
And it found an 84% yield.
Right.
But then the researchers threw a major curveball.
They did. They asked the robot to optimize a completely different but structurally related molecule, product 15.
Normally, an AI would have to start from absolute zero again, right?
Yeah.
Dropping those random parachutists blindly into the fog.
But not here. The AI used a multitask Gaussian process, or MTGP.
MTGP?
Right. It remembered. It took everything it learned from the topographical map of product 12 and applied it as the foundational starting point for product 15.
Oh, wow. And because it transferred that learning, the robot found the optimal conditions for the brand new molecule in just 4 iterations.
Just 4?
4. It hit a 90% yield almost instantly because it already knew the neighborhood.
Exactly. If we connect this to the bigger picture, it changes how we view failure in the lab. Usually, a failed experiment goes into a notebook and is just forgotten. With transfer learning, every single failed experiment becomes highly valuable training data that speeds up the discovery of the next entirely different reaction.
That is incredible. And they push this to the absolute limit in their final case study, right? And an antioselective photocatalytic cycloaddition.
Yeah, that is a massive, incredibly complex chemical space.
Because they weren't just looking for a high yield this time.
No. They had 3 competing objectives to satisfy simultaneously. They wanted a high yield, a specific diastereomeric ratio, and a specific enantiomeric excess.
Okay, let's put that in simple terms for everyone.
Sure. They wanted a lot of the product, and they needed it to have the exact correct 3D geometric shape, specifically avoiding its mirror image.
Like getting a right-handed glove instead of a left-handed one.
Exactly. Trying to optimize 3 vastly different physical properties at once would break a normal algorithm.
So what did they do?
They didn't use a normal algorithm. RoBrains trained 3 parallel surrogate models.
All at the same time.
Yes. Each model acted like an obsessive specialist, focusing entirely on just one of those 3 goals.
Okay.
Then, a master algorithm called log and pergo combined the recommendations from all 3 models to find the mathematical compromises that satisfied everyone.
But if 3 models are working simultaneously, how do you stop them from accidentally suggesting the exact same experiment?
They applied a Euclidean distance filter.
Okay, Euclidean distance is just the straight line distance between 2 points in a mathematical space, right?
Yes. So before the robot actually runs an experiment, this filter mathematically checks the physical parameters of the proposed tests.
Okay.
If 2 tests are too similar, if the Euclidean distance between their parameters is too small, the filter rejects one.
Ensuring every single droplet of chemical is used on a distinct, informative test.
Exactly.
And the result of all that, computing power. It found conditions that produced greater than 99% yield and greater than 99% of that exact 3D geometry they wanted.
All while using less catalyst than the leading literature benchmarks.
That is just stunning.
It is.
Time for our final mini recap.
Let's hear it.
Bullet 1. Transfer learning allows the robot to use data from past experiments to solve new, similar problems almost instantly.
And bullet 2. Complex algorithms can manage massive chemical spaces to satisfy 3 competing goals simultaneously.
So our final interactive question for you. Imagine how much faster global drug discovery could be if you had thousands of these $5,000 robots sitting in labs around the world, all sharing their transfer learning memories through an open source cloud.
It's a staggering prospect. I mean, what RoboChem-Flex essentially proves is that the future of automated chemical discovery does not require a multi-million-dollar facility.
Right.
By leveraging highly advanced software, noise-aware algorithms, hyper-volume optimization, and transfer learning, you can almost entirely compensate for the physical limitations of cheap 3D printed hardware and noisy DIY sensors.
So what does this all mean for the scientific community at large?
It lowers the buy-in.
Yeah. Modern science has kind of felt like a high-stakes poker game where you need $100,000 just to sit at the table.
Right. And this platform lets anyone pull up a chair.
Which is beautiful.
And that raises a profound question to leave you with.
Lay it on us.
If a $5,000 machine made of high school electronics and printed plastic can autonomously optimize complex pharmaceutical building blocks, what happens when community colleges or even ambitious high school chemistry clubs start discovering previously unknown chemical reactions?
Oh, wow.
Does the democratization of this AI technology fundamentally redefine who gets to be called a scientist?
It's a completely new paradigm. The Matthew effect, the rich getting richer finally has a real counterweight.
It really does.
You don't need the massive budget anymore. You just need a 3D printer, some open source code, and the curiosity to ask the right questions.
Exactly.
Thank you so much for joining us on this deep dive. Keep asking those questions, keep exploring, and we'll catch you next time.